Thank you, sister, because it does. It does look like the coins. All right. Experiment number 2 was deal until you get hearts. The equation we just got, y equals 21 times 0.7 to the x power. X is the number of trials. Y is people remaining. Now let's think about this. We started with 20 people dealing cards to themselves. 20 people dealing cards to themselves. That's why I was so excited about 20, because it's a nice number. And because of the number of suits in the deck, it's a perfect number to use. We started with 20. Now your model, unfortunately, came out with what? Is that perfect? No, it's a best fit. It's a best fit. It's not perfect. It's close, though. This number 21, or this number right here, which I've now partially erased, unfortunately, because of Excel. These numbers that were, this was 53 to the x, and this was 55 to the x. These numbers out in front, these 21s, 19s, and 21s, those we're going to call initial amounts. This coefficient out front, that tells you what your experiment started with. Number of people turning cards, number of people flipping coins. In a second, it'll be number of people in America. It's whatever you start with. This is your initial amount. This is your initial amount. Later on, I'm going to have you guys analyze my old lead singer who used to drink 3 and 4 Red Bulls at a time. That'll be the initial amount of caffeine in his body after he drinks 4 Red Bulls in 5 minutes. Thing of beauty was. But whatever that amount is, when you take aspirin or Advil for pain, you pop 2 500 milligrams of Advil, your initial amount of Advil in your body is 1,000 milligrams. From then, your body starts getting rid of it at a set rate, which we'll get to. That's part of this too, is dealing with that kind of stuff. So whatever that number is out in front, your TI calls it A, I think. I think they called it A in that. Yes, that's the initial amount. That's your initial amount. Boom. This is A. Now the TI doesn't know there were 20 of us in the room. It doesn't know there were 20 of us in the room, so it best fits it to 21. Hey, it's all good. It's all good. We only ran 8 trials. If we ran 8,000 trials, it would smooth out a lot more. I'm stoked we got it after 8. We got that close. So now my question is, what's the 0.7 here? And or what's the 0.5 over here? Because this goes back to what Aaron's question is, or comment was. It looks like the coin flip. Go ahead, my friend. What is it? What is it?
Me?
Yes. I thought you were going to tell me.
Oh.
Maybe you weren't.
No.
You weren't.
What did you ask?
I asked what the 0.7 is. Michael?
Is it the amount of people that drop out for time?
It's not an amount.
Rate.
It's a rate. It's a rate. So 0.7 is 70%. 70%. 0.5 or 0.53 is 53%. So it's the percent that are remaining. Now think about why that makes sense. Let's think about why that makes sense. Everybody's like, okay, I got it, sweet. There are 20 of you pulling cards, yeah? On average, how many of you should pull hearts? On 25% or 5 of you, yes? So 25% of you should pull hearts, which means 15 out of the 20 or 75% are still pulling, which means you should pass on 75% to the next round. And then after the next round, you should keep 75% of those that are pulling cards. That's why it was important to put the cards back in, to maintain the 75%. So the next round loses 25%, keeps 75%. Next round loses 25%, keeps 75%. Eventually it's going to whittle down to nothing, as we saw. Theoretically speaking, it goes on forever though. So basically, these numbers in here are the rates. And in this case, I'm going to put it in red. These are the rates of change from trial to trial. And if you want to use the word change, you can also use the word retention, if you will. We're retaining Now, the TI got confused. It thinks it's 70%. It should be 75%. But remember, it's a best fit. We didn't give it perfect data, did we? We gave it imperfect data, and it came up with 70%. That's not bad. That's not bad. 70% is actually what we were showing. We weren't showing the perfect 75%. The only way to show the perfect 75% would be for us to do the trial infinitely many times. That's the only way we'd have to do it. Now, you get very, very bored doing that, of course. So, yes indeed. So the idea is, when you have an exponential model like this, you get these two values that are given to you. You get the base amount, the initial amount. That's what you start with, once again, full in the pocket. This guy. And then the percentage amount. And that percentage is the amount that remains. The remaining amount. The retention amount, whatever word you want to use. It's that remaining amount. You're keeping 75% each time. You're keeping roughly half each time with a coin flip. Well, hopefully that makes sense, because you're losing half each time. Every time we flip a coin, half are heads, half are tails. Now, when I say half are heads and half are tails, that's not entirely a true statement. It's not every time you flip a coin, half the time it's heads and half the time it's tails. It's in the long run, when you flip a coin, half the time it's heads and half the time it's tails. It doesn't guarantee heads, tails, heads, tails, heads, tails, heads, tails. It guarantees a set proportion over time. Does that make sense?
How much time do you need to come up with that?
That is a fantastic question. Kelly, ask it again.
How much time do you need to know that that's the variance?
How much? Can I answer the question with a graphic instead of that? Okay, if you don't mind. This is a very, very good question that begs an extremely good. I've actually designed a few demonstrations to show. There's no exact answer to it, because experimentally you're never going to get to exactly 75%. You can't, but you're going to get as close as you need to get to it. Much like the same way, when you take 1,000 milligrams of Advil, your body never gets rid of all of it. There's always a teeny tiny little amount somewhere in your body. But it's such a little tiny amount that it doesn't matter. I mean, it might be 0.00000 times 10 to the negative 18th grams. But that amount is so minuscule that your body doesn't even think it's there. So you can never zero it out, but you can get as close as you want to get to it. Now let me demonstrate up here, if you don't mind. It's a fantastic good question.